The Empirical Energy Podcast blows open the silent revolution, rewriting the rules of global energy markets. Measured, verified energy is no longer an alternative. It's becoming the gold standard. We dive deep with the producers, traders, consultants, and renegades driving this seismic shift. Step inside the raw mechanics of how verification and blockchain-fueled trading are dismantling the old systems and creating a future where alternative energy doesn't just compete, it takes over. This is the movement of reshaping energy as we know it, bold, unstoppable, and just getting started. Here is your host, Mark Smith.
Hey, welcome everybody. This is Mark Smith, your host of Empirical Energy Podcast, and I'm here with Emily Wilson, who's on our Clean Connect team. Welcome, Emily.
Thank you. Nice to be here.
Yeah, so these early episodes, we're talking to our team because we really want to set the foundation for empirical energy. And Emily is an expert in basically the science of measuring emissions and all that kind of stuff. So Emily, why don't you talk about your role at Clean Connect and your background, which is fascinating.
Sure. Yeah, no, I'm happy to. So I just joined Clean Connect a few months ago, and I'm heading up instrument development. My specialization is developing instruments for measuring trace gases or other systems. And my background, I've had an interesting background, 20 years. I spent the last 20 years, actually 23 if you include postdoc, at NASA Goddard Space Flight Center, developing instruments that measure trace gases for Earth and planetary atmospheres. One of the highlights was sending an instrument into orbit. We launched carb in 2019. It went via the space station, so that was pretty cool. But I think my real trick is, so for instrument development, I develop inexpensive technologies. So not inexpensive as in cheap, but so that they are scalable. My ultimate goal in life was to develop a global network of ground instruments that measure greenhouse gases so that you could reach areas like sub-Saharan Africa where there are no observations. NASA does a really good job of measuring greenhouse gases, like with Orbiting Carbon Observatory 2 and such, but there are areas that you miss. So when you have like areas of like kind of dense cloud cover, and the satellite passes at the wrong time, you may totally miss that observation. So my view was, okay, let's build ground instruments that, are passive. They point at the sun, they measure the absorption of these gases in the infrared, and then make them inexpensive enough that you can put them in developing countries and you can basically put them everywhere. And then you can have a global carbon observation all the time. So anytime the clouds clear, suddenly you have an observation. So that was my goal. And that was an instrument that I developed called the miniaturized laser heterodyne radiometer. And that got pretty far. I patented it. We have a number of instruments. We have one in Edinburgh, Scotland. We have one that was going to go into the Amazon. I think what we struggled with, though, is commercialization and mass producing it, because NASA, we can build something clever and we could say, we can write a paper. We could say, hey, this could be used for something, but we couldn't really implement it. We couldn't do much beyond like maybe a partnership agreement. But I did a partnership agreement with Clean Connect a couple years ago to license this patent because it can also be used for measuring gases in combustion systems. And my background before I went to NASA, my graduate work was in combustion. So I measured gases from different approaches. It depends on which gas you're measuring, right? You don't want to measure, every approach isn't right for every gas or every situation. So your goal is to pick the right instrument approach and then measure, like, for example, if you're measuring nitric oxide, that's a different approach maybe, or something with a low concentration, maybe use something like cavity ring down. Anyway, but yeah, so my background was in combustion and spectroscopy. And and then I worked at NASA and I just retired and I moved on to Clean Connect. And I'm really excited because now I could do more than develop an instrument and write a paper. Now we can mass produce it. We can actually improve emissions. We can reduce the emissions. So that's super exciting.
Yeah, in fact, I think we have some clients who need to do increased stack testing, right? They're in Colorado, the regulations, whatnot. And they were paying us to basically set up all these different camera systems to look at the stuff coming out of an enclosed combustion device and different things. And yeah, the OGI camera, which is our main thing with monitoring, was just not going to cut it. So I remember David, my business partner, David Conley, who you'll meet on another episode, he started searching, looking frantically for something. And I don't even know what he put in the search thing to come up with your white paper on the laser heterodyne radiometer. Hope I said that correct.
You did.
But
Very good.
he found, and he said, wait, who's this person, Emily? And he found you, and you're a real person, and you're working in NASA. And you said, did you know you could actually license this thing and we could bring it to life together? So that was great. But I was also excited the changes going on that you did call up, and you said, I think it's time for me to move on from NASA. And it worked out great. Now you said you have your labs there in your background, and you're working with Remington and his lab, and who I call Remington, he's kind of like our MacGyver, right? With your design, and between the two of you, you could put some interesting stuff together and bring it to market. So we're super excited to see your brainstorms come to life.
He's great at troubleshooting. Yeah, I love working with Remington. Yeah, it's so exciting to be able to say, okay, let's actually solve this problem in real time. That's actually my preferred way of instrument development. The nice thing about this is we don't have to have, and this is not in any way a complaint, but different places do things different ways. So we do not have to have 15 meetings. We can say, okay, let's come up with this design. Does this meet the requirements? Okay, let's build it. Like right now, let's buy the parts, let's do it, let's test it. And that is excellent. That's exactly what I like to do. That is perfect. I just want to I want to create the idea, buy the parts, build the thing, test the thing, manufacture the thing. That's the key part. And then we can get it into use. So that's very exciting.
And when we're talking about that specifically, and we've mentioned this publicly before, but we have this thing that internally we're calling Project Vulcan. So tell me more about Vulcan, because I know even before you were on board at Clean Connect, you got to meet with some of our clients and just say, hey, here's what this Project Vulcan is all about. And so far, everybody said, ooh, I want that. Tell me more about it.
Yeah, the point of Project Vulcan is to measure emissions from stacks. Now, the thing, and more than that, once we have emission measurements, use a feedback loop to input what these concentrations are. My goal is to map the burner, right? So you see the gases mapped across the stack. And then you can say, oh, this is burning a little rich, this is burning a little lean. And then you can change up the parameters in real time and reduce emissions. And if you can do that, David and I talked about this early on, maybe you can reduce greenhouse gas emissions by maybe 10%, maybe more. And that's actually putting the technology into use immediately. So stack emissions, so we developed an approach to map the emissions. So not just technology wise, but also just like, where do we sample so that we can create a model of this, see how it's burning, and then use these parameters as a feedback loop. One of the things we initially talked about the miniaturized laser heterodyne radiometer for measuring emissions, drawing a sample out in various places. And we can do that. And that's great for gases that are products of incomplete combustion that have like lower concentrations, so carbon monoxide, that's a good candidate for that, nitric oxide. But for some of the gases where you get it, like the primary combustion equation results in CO2 and water vapor, right? So those are your primary gases that you're going to be measuring, and methane, of course, because methane's a product of incomplete combustion. The goal is to measure all of these simultaneously, and so the thing about spectroscopy is you are measuring these gases by measuring their absorption of their rotational vibrational transitions, right? For example, carbon dioxide, it's a linear molecule. So you have two O's and a C at the center, right? And they rotate and they also vibrate. And that's why they absorb infrared radiation. So what we're doing is so you take that, and so your signal, you create a signal, you do a scan, what's called a scan, right? And a scan is basically this. You are putting a laser through a gas sample and you are scanning it. And that is better than a camera because you can look at individual rotational vibrational transitions and you can see the depth. And the depth of these transitions is proportional to the concentration. Without going into a ton of spectroscopy, it's a good approach that's been done for a long time, and it can get you really high resolution results. So let's say your cameras pick up water vapor. Okay. And I know they do. And they pick up some other interferences too. When you do a scan where you look at each individual rotational vibrational transition, you do not have to worry about that because you know where they are. They're in known locations. So you're like, oh, that signal is going up because of some other CH stretch or something. This is like ethane or something. We know that's not methane, or this is water vapor. If you have a high resolution scan, you can identify what all the interferences are. So that's what we're doing. We're basically going to target each molecule roughly what it's the dynamic range. The dynamic range is what's it naturally occurring in, right? Is it between, for example, 100 ppm parts per million and like 10,000 parts per million? So if it occurs in those ranges, depending on where you are on the stack, you need an instrument that can measure all of those ranges. So we're doing so laser heterodyne radiometry is good for very low concentration molecules, but just tunable diode laser absorption spectroscopy is good for other areas. But I think where we really shine is our mapping technique. We're going to map the whole exhaust, and we're going to be able to use that as a feedback loop.
So essentially, the big payoff for people is we could put this inside maybe the bird's nest type of device, sits on top of the ECD, and for about the price of a stack test, they're getting continuous.
They get continuous, and yeah, and it actually doesn't have to be located within the bird cage. It can be somewhere else, and we can just draw samples, and then but they'll get a ton more information. And what that really means is when you make a burner more efficient, you're saving money. You're using less fuel, you're putting less greenhouse gas emissions out. So the more efficient combustion you can make the system, the better you're doing.
And like any other thing, as we get into what we call Prove Zero, and we'll learn more about that in other episodes, where we're measuring everything in real time on a site, the more instruments that we have, the more we're not guessing what's going on, and we don't have to use like the Promax process simulation to say, what's this thing doing? We are actually directly measuring that. And again, over time, we see sites being engineered with way more direct measurement because it's more accurate and it can be done at scale. And that's what we're working on. Thus, the empirical energy. It's literally not, we're not guessing, we're not using emission factors, we're not doing any of that stuff, which everybody agrees is worthless. And quite frankly, I think has caused, I shouldn't say worthless, but it is so wildly off that people don't trust it. And in fact, there's geopolitical things that are going on in the world today because they don't require empirical measurement. They just require, hey, let's just use some factors from IPCC, okay, instead of actually measuring it. So anyway.
Regulations are meaningless if you can't actually make a measurement. If you can't make the measurement and know how you're doing, and companies want to know how they're doing. So yeah, it's an exciting area that I think a lot hasn't been, I think it's an emerging area.
Yeah.
But also the technology wasn't always there. So one of the devices I'm working on, one of the instruments, I'm struggling to find components at the right wavelength because they just don't exist yet. So we're looking for workarounds, but it's exciting. It's a fun time.
Yeah, because I've seen some of the pictures, the images you've had of some of the original devices you built, and they're little mini houses. And now you're trying to say, oh, now we're going to shrink that down to a size that makes sense. Yeah.
The latest instrument was, so the CubeSat we sent up, which is about the same size as the mini LHR, is about the size of a lunchbox. We wanted to call it lunchbox for a while, but the Air Force didn't like that name, which is funny. Yeah. We had a bunch of different names that we thought were hilarious. And when you're a scientist working in a lab for long hours, you want something funny. But anyway, we agreed to mini carb, which sounds like a diet plan you don't want to be on. But anyway, yeah, it's about the size of a lunchbox. 2U is the smallest form factor. Now, a U is 10 centimeters. It's like a cube, right? 10 centimeters by 10 centimeters. So if you're 2U, it's pretty small. And the one we built for ground measuring fits on a backpack, and we made it completely operatable, like with solar panels and a battery, so that in case you were out in the field and you had no electrical hookup, you could just turn it on and run it. So
interesting. And I know you and I were both working on abstracts for ADIPAC, organizing that show and whatnot. And our Middle East guy said, hey, I need one on OGMP, which I wrote, another one on their EPA approval, and I put one on empirical energy. But then you put several together. And
yeah, I ended up with two. Yeah. And they were both for things so one of them was for stack I'm sorry, no, it was for open flame flaring. That one is, I have an approach for measuring emissions of gases for that. And that is not something that's being done right now. And it is it's an approach, I don't want to spill it, but it's an approach that has not been used in the combustion industry before because they thought this approach was too slow. They thought the response time compared to a flare event was too slow, but but they didn't know all the iterations of this instrument. And I did, because I knew from orbiting Carbon Observatory 2 that you can do this approach, and somebody could Google that indeed, but you can do this approach where the scan is instantaneous. And actually, it's just as fast as your response time. So you can do dozens and dozens of scans, and you can get high spectral resolution observation. It's not water vapor, you know if it, or you do know, if it's water vapor or methane, and you can get concentrations of each. And that's going to be exciting. And actually, it's not new technology. If anybody does a literature search, I firmly believe in literature searches to understand who's done what. So they first started measuring methane in a flame in 1957 over at NIST, but it wasn't called NIST at the time. It was National Bureau of Standards. Anyway, so you can go look through the archives. And they were like, okay, that scan's too slow. You can't do that. But you can do it fixed. And also with CCD cameras now, you can do it. So anyway, it's very exciting. So I've been looking for CCD cameras all day. Oh, that's the stack testing one. Yeah, I did two. The other one was for the stack sampling that we talked about.
Yeah. Okay. So Emily, let's just future pace. Let's say we're successful with the stuff Clean Connect's doing, the stuff that you're doing. What happens? Why is this exciting to you? And what part of your personal mission and the bigger mission do you think could happen as a result of all this?
There are two things. One is we can absolutely reduce emissions from combustion sources. That's huge. If we can reduce emissions fast enough, then we can reduce we are not contributing as much to the global mean temperature rise. So one of the things is every time the global mean temperature rises just a little, it ticks up. We have other issues that are snowballing, like, for example, thawing permafrost. In permafrost up in the Arctic regions, methane and CO2 are underground. They're frozen, right? And it depends on what kind of biologic activity, whether it's more methane or more CO2. So if there wasn't any oxygen, they produced more methane, and if it's more oxygen, they CO2. But either way, these are serious greenhouse gases. CO2 is a greenhouse gas, but it's not as strong absorbing as methane. Methane is a much more serious one, so the concentrations are more important. But anyway, they're both important. So if we can reduce emissions, we can stop the endless cycle and the snowball effect of climate change. That's number one. And also the other thing that, like, a personal mission is, I would like to manufacture the mini LHR for global ground measurements. That's something I would like. The instrument already works in this configuration. It's inexpensive to build, so we could send it to developing countries, and we could so if you aren't monitoring it, how do you know how well you're doing? So if you don't have a global number for CO2 and methane, how do you know? You need it. And yes, they have inputs. Yes, there are people doing this research all over the world, right? They're measuring, but in the atmospheric column is where the mini LHR, and what the atmospheric column is from the surface to the top of the atmosphere. So we need that kind of measure as an input to some of the atmospheric models. And then, so if you get a global measurement, especially in places that are missed, you know how well you're doing and you can track it. You can't track something you can't measure. So those are the two things that I think we can really do. We can actually reduce the emissions, though. That's huge. This is more than I can write a paper saying, hey, you could do this. No, we're going to do this. That's amazing for me.
Yeah.
That is my whole reason for being.
And for me, being the EPA cheat sheet guy and someone who had to really understand thousands of pages of regulations, which are all being reconsidered right now, the reality of it is, I look at some of the stuff we're doing and providing that feedback loop, and what's happening with the customers we already have that have this empirical measurement. It's almost gamifying the thing in the sense that they're incentivized to reduce this stuff in a very rapid pace, and they're ending up achieving all these 1,000-page regulations without the regulations themselves. In other words, we've given them the feedback loop that they can actually use to make these changes in near real time. And obviously with AI, we can eventually develop instrumentation and feedback loop that could just make these adjustments automatically.
But don't forget, so our regulations might be in flux right now in the US,
Yeah.
but overseas, not necessarily. So don't forget, we could have markets for some of these things overseas as well.
Yes, absolutely. Yeah.
EPA regulations they're important from my perspective and your perspective, but also, there are other opportunities too.
And empirical energy honestly is the stuff we're talking about, this empirical energy is going to be the basis for scaling alternative energy all over the world. And I'll make that case in subsequent episodes and things like that. But anyway, Emily, it's super exciting to have you on board.
Thank you.
And to see if to actually help you and help us achieve our mutual mission together, bringing science and AI and blockchain and all these things together to make this possible. So thanks for being part. Yeah.
Thanks. I'm having the most fun I've had in years. I'm really excited to be here.
Excellent.
The Empirical Energy Podcast requires more than a conversation. It takes action, research, and collective wisdom. If today's episode resonated with you, we'd love to hear your insights. Join the conversation and help us shape the future together. We'll be back with more stories, strategies, and real-world solutions that are making a difference for everyone. In the meantime, be sure to subscribe, rate, write a review, and share it with someone you think would benefit from it too. Thanks for listening, and we'll see you on the next episode.